probably the biggest advances in the field in the last 2 years. For the kinematics topic, we will talk about channel maps again. You've seen the channel maps before, but again, a bit more detail on them. And then all the different types of studies you can do with kinematics. So vertical structure, orbs, hinge, turbulence, velocity, you can see dimensions, and circumplanetary disks. Okay, so recall from the Leiden mission that molecules can get excited by collisions and then emit a molecular line. And we've so far talked mostly about CO emission and I mentioned ASD emission, but of course there are many, many other molecules out there. So not all of them are detected in disks, but in interstellar space, I think there's hundreds and hundreds of interstellar species by now. So why we want to study chemistry in disks? So this is kind of part of this cycle of how did life start on a planet, at least on Earth, maybe on other planets, where these molecules become larger, become more complex, actually being able to form amino acids, DNA, and other biomolecules that they live in life. And related to that, like basically a step back, is the composition of exoplanet atmosphere. So maybe not so much forming life, but still the question like, can you have oxygen on another planet? Carbon dioxide? Yeah. So or water, any molecule that may be ending up in an exoplanet atmosphere. So generally, people are scared of astrochemistry because it sounds like something super complicated. And I think many of us remember chemistry in high school. So I can start by telling you that astrochemistry is very simple compared to chemistry in high school because space is really empty. I'm going to show you the numbers in a moment. So when we talk about doing astrochemistry, we don't. The chemical processes itself are not really the most interesting part. The chemical reactions, they will happen with a certain rate, and we can simply put that in mind. But the reason why astrochemistry is interesting to study is because molecules can be used as a diagnostic of many different properties. Of course, gas density, what we talked about this morning, but you can also use it as a diagnostic of temperature, ionization, using kinematics, but we can also think of radiation fields, where like what I mentioned earlier this morning, the cosmic ray or X-ray rate can be determined from the emission of molecules. Also, like more on a fundamental level, why molecules are important, they are actually coolants of clouds. So that means that they drive the collapse itself. So if there were no molecules, there were no stars, no planets whatsoever. So it's more fundamental why molecules are good to know. And then finally, so the molecules form the start of complex organic life. We also call complex organic molecules, we call them comps as well, and biomolecules. And finally, because the universe is so empty, the chemistry there can be quite exotic. Like there are molecules found in the universe that are actually really hard to form on Earth. So you have a unique chemical laboratory with very special conditions. And sometimes we find crazy molecules that are really hard to form in Earth conditions. So we can only figure out what they are by doing it in the lab. So this is again more from the scientist perspective. I study astrochemistry because we can. Okay, so in terms of timescales, just to put things in a bit in comparison, like how quickly are chemical reactions. So typical collision time of molecules is about 1 month in a density of 10 to the 4. So this 10 to the 4 is the density in a dark cloud, right? So while the cloud is still collapsing. In a disk, it will be, the densities are up to 10 to the 8. So things will happen with this fast. Molecules don't collide very often. So that means that the sort of chemical time, the time that it takes to change the chemical condition is like 10 to 5 years. And then star formation and lifetime of clouds is more than the order of millions of years. So chemical timescales are relatively short compared to the objects that are looked at. Initially, people did not expect to find many complex molecules or many extended molecules in space because of this Baumann's timescale in cloud conditions. Chemical reactions are slow. And so when the first molecules were detected, it turned out that there was a very rich chemistry, which means that we needed to consider additional physical conditions that would explain that chemistry, and I'll come to. So the first the first gaseous molecules were actually discovered in opticals, CH, CN, CH+, in like the 30s and 40s. And then the first models trying to explain these detections were developed in the 40s and 50s. So this is still pretty long. Then with the development of radio astronomy, another group of elements and molecules became available in the centimeter wavelengths, like H1, OH, NH3. NH3 was like the first molecule that consisted of more than 2 atoms, water, in the 60s. Then eventually UV astronomy was developed, which meant that we could suddenly detect these 2 lights. And then millimeter astronomy really do things up, because it started with the detection of CO, which we've seen this morning in millimeter astronomy. But later, with more sensitive telescopes, we started to discover more and more molecular transitions in millimeter wavelengths. So here, just as an example, this is a spectral line survey in the star-forming cloud Orion. And as you can see, there are many lines, so the frequency range is 200 to 260 gigahertz. And as you can see, there are many different features all related to different molecules. Then infrared astronomy also started to contribute to astrochemistry. So IRAS was, well, we talked about that before, it was doing infrared photometry, so it measured. They did a full sky survey at various wavelengths, which meant that we now had some idea of the typical cloud properties in the dust. And then, sort of following that, ISO in the 90s started to do spectroscopy. This should have been micrometer, because that got corrected by Theo. So 200 micrometer spectra. And then they actually discovered water, OH, O1, far infrared lights in many of these clouds, and also maybe larger molecules. And in 2000, Spitzer was again targeting specific clouds and disks. They found particularly ices and silicates. Was not really high enough resolution to observe really complex chemistry. Herschel in the far infrared was able to measure many, like multiple transitions of CO. Also detect water and HD in protoplanetary disks and many other molecules. And of course, with the launch of JWST, we hope to find even more molecules in the future in the infrared. So, but in this talk, I will only focus on the millimeter results, the ALMA results. But just so you know, infrared is really significant as well. What's important about infrared astronomy, though, is that you don't resolve the disk. These are all single disk observations. So you just have a spectrum, and you have to infer from that spectrum what part of the disk the emission originates. Okay. So chemical reactions. So because of the low densities and also low temperatures, chemistry is controlled mostly by two-body reactions. So you don't really have significant three-body reactions. So this is actually non-tail densities. I had a slide with densities, but I think that's skipped over. So remember, in disks we have densities up to like 10 to the 8, 10 to the 9 in the midday. And in clouds it's like 10 to the 4. So three-body reactions, so three molecules colliding with each other at the same time, doesn't really happen until you get much denser. So we don't really consider two-body chemical reactions. Two-body reactions result in, of course, different abundances of molecules, and they all depend on physical conditions. And a reaction rate is described by like a constant K, and then the density of molecule X, the density of molecule Y, and then per cubic centimeter per second. And this parameter K is usually temperature dependent. Okay? So this is how a typical chemical reaction network looks like. We're not going to go through it in a lot of detail. This is the carbon network. So this tells you if this molecule gets hit by an electron, you get CH. If that molecule gets hit by oxygen, it becomes CO, etc., etc. All of these different chemical reactions have their own reaction rate, their own K number, sometimes as a function of temperature. So you can imagine that calculating through a chemical network is not something you can do by hand. You really need to let it do by a computer. Here's another example of a chemical network now of oxygen-bearing molecules. So also here, you essentially can see, like, if you start with one molecule, if you add something, what do you get next? So types of chemical reactions. There is sort of the formation of bonds, like creating larger molecules. Can be, for example, if you have one element, sorry, one molecule plus another molecule, when they merge together, you also emit photons, so like radiation is created, energy is created. You can also have a combination of an ion, where the molecules or the atoms merge together, but then an electron is emitted. And you can also think of grain surface reactions. So this is essentially if you have one molecule in gas and one molecule frozen out into a grain. Maybe when they react to each other, when they merge together, they become separate from the grain, or they stay together. Other than formation of bonds, so creating molecules, you can also struck bonds, so kind of the same with dust, coagulation and fragmentation. So a molecule that gets hit by a photon, HU, with the energy HU, will dissociate in separate components. We've already talked about this a lot, of course. You can think of, and the same thing would happen if it gets hit by an electron, that's called dissociative recombination. And finally, you can even think of a collision where essentially one molecule hits another molecule and just breaks it. And finally, you have rearrangements of bonds. So this is, one charged, one ion molecule transfers its positive or negative charge to the other one. So just to give you an idea of what type of reactions exist. Okay, so then about excitation. So the chemical network, the chemical reactions are just the things that control what are the abundances. But then as soon as you have an abundance, there is this additional process of excitation determines how strong the lines are. And we generally assume in a disk local thermodynamic equilibrium, or LTE, which simply means that the collisions lead to excitation, and then photons are emitted spontaneously. And this, in LTE conditions, the distribution of the populated energy levels, remember molecules having different energy levels, is described by the Boltzmann distribution, which is shown over here. So it's like the density of the population upper energy level divided by lower energy level is described by G, which is the GU and GL. That's the degeneracy of an energy level. So essentially how many possible ways there are to be in that energy level times this exponential minus the energy divided by the temperature. So essentially, this population, the population itself is set by the temperature. That's why it's called thermodynamic equilibrium. And just to clarify, what does this mean? So this, well, first of all, the HU, the energy of the photon, is set by the difference between the energy of upper energy level and lower energy level. So the difference between that sets the energy of the photon and the frequency of the photon. So what are these upper and lower energy levels? Well, you have actually heard me use these terms already quite a bit. So for example, for 12CO, we have all these J levels, 0, 1, 2, 3, 4, 5, like going up to 40, I think. And each transition from an upper to a lower has a specific frequency, a specific fingerprint, and a specific upper energy level. So you can calculate that the transition from level 2 to level 1 has this frequency, and that is essentially equal to the difference between 17 Kelvin and 5.5 Kelvin. If you want to find more of these numbers, so the rest frequencies of molecules and the upper energy levels, go to this website called Sterrewacht, where you can find them. Okay, so say that you have measured the molecular line, and now you want to calculate the corresponding column density of that molecule. So there are two steps that you have to take, because of course what you're measuring in that line transition is only the number of molecules that were in state U, in that upper energy state. That equation is actually, it's relatively simple. So you have a 4 pi, you have the flux, so the flux that you measured, the line width, the emitting area, so these are all observables, HC are constants, and then you have this coefficient called the Einstein A coefficient, which is again a property you can look up on Splendor. It's a property of the transition. So essentially the higher the Einstein A coefficient, the more flux you need to, so essentially the fainter the flux is going to be. So if the Einstein coefficient is low, that means that the flux is expected to be higher for the same column density, right? Okay, so now say that we have calculated that number, that column density, the population in that upper energy level. We can now calculate the total column density using this equation. So this is that actually summing over all of the energy levels in the Boltzmann equation. And so the total column is written by NT. And you calculate it from the column that you just measured divided by the degeneracy. The Q partition function is again a property of the molecule. You can look it up. This is what describes the relative degeneracies of all of these levels. So this is the result of that summation overall. And then, like I said, there's this exponential minus EU divided by K times the temperature. So, in order to measure column density, you have to assume a temperature. And then for the rest, it is, and look up a bunch of constants, and then make sure you check your units. That's always a very tricky part. But then with that, you can in principle measure a column density of a molecule in a pretty straightforward way. Well, one of the big uncertainties in this calculation is, of course, that temperature. Like, what is the temperature of my emitting region, which you may not know. And something that is often done is using a so-called rotational diagram. Because remember, the emission strength really depends on the combination of density and temperature. But you will need more than one transition in order to disentangle the two. And that's what you do in a so-called rotational diagram. So remember, you have this equation, you have this upper energy level, and so say that we take the logarithm of this equation on both sides, it will look like this. And if you look at it, you can see that you can essentially describe this as a linear fit. So you have your y value, so the thing that goes on the y-axis. This is the thing that you measure, right? It's the flux times some constant that gives you the end column density. As a function of x, which is the upper energy level of each transition that you measure, times 1 over the temperature. So that's the slope, plus a constant, and that is your total column. So say in this case they have like a bunch of different transitions measured, all the different energy levels, they fit a line through this, and then the slope of that line gives you the inverse of the temperature, and the constant of that line, the offset, gives you the total column. This is where this is how a lot of these calculations are being done. Okay, then switching to some more like chemical properties. I've already mentioned several times that molecules can freeze out onto dust grains. I'm mostly talking about CO, but of course this applies to any molecule that freezes out onto dust grain. And it's so molecules freeze out whenever the temperature is below the freeze out temperature of that specific molecule, and that means that you can get really complex icy layers onto these dust grains. And what's really cool about it is that this process actually enables more complicated chemistry, because you have these molecules of ice that can then be bombarded by, for example, hydrogen atoms or additional radiation fields, and they reaction rates or essentially the reaction processes are different and sometimes much faster than in the gas phase. So to show some examples of that, so initially you would have freeze outs or absorption onto dust grains. You have the simplest elements and molecules. Then through addition of atoms, so like hydrogen, for example, or oxygen, photolysis or radiolysis. So this is radiation fields. Sorry, I don't know how to pronounce that. You can form more and more complex molecules. This has actually been confirmed in laboratory experiments that this really happens. So this is not just science fiction. And then at some point, these molecules may actually sublimate again, either as a result of temperature or as a result again of radiation. And what is particularly interesting there is that CO freezes out at about 20-30 Kelvin. We talked about that before. So it needs to be, so it means that it evaporates really quickly. But if you then form more complex molecules, they will evaporate at much higher temperatures. So you may end up with a completely different chemical composition than you started with. So essentially, ice chemistry enables more chemical complexity. So what is the observational evidence that ice chemistry is really happening in space? Well, we can measure ice absorption spectra in the infrared. I guess I was lying before. I do have some infrared chemistry in this one. So this is an example of that. So there's the flux as a function of wavelength in the infrared. And as you can see, you have all these absorption features here that can all be associated with ice molecular features. Since this is absorption, it means that you essentially have a cloud of icy dust grains in front of something that's very bright, like a star. So most of these are actually ice compositions in clouds around stars. With data OST, we hope to do similar measurements with that of protoplanetary. And then this picture, and ISO did some of the brightest. Even they did some of the brightest. This data OST is going to do much worse. So most of those pictures actually was actually in clouds.
And why is it continuous?
Why is it continuous? So this is
with the red one and the blue one.
Oh, well, there's no features there. You see, they're just not as prominent as in these other bits.
No, but over the eye.
I don't understand, sorry.
Maybe the gaps.
Yeah. Oh, these
Big
gaps.
ground base and Spitzer.
Oh, yeah, because these are, no, the ground base refers to this part of it, to this part of it. So this is wavelength coverage by Spitzer, starting at 5 micron. Spitzer couldn't observe at shorter wavelengths, and from the ground, you can only observe up to 4 microns. That's why you get a gap. I guess in the one here in the top, I don't know what they did. That may have been another facility where they were. Yeah, that's it. Yeah. I guess for. Oh, sorry, the black. Yeah, the black spectrum was taken by ISO. ISO did have coverage down to 2 micron, but Spitzer only had coverage down to 5 micron. So yeah, it's just the property of the instrument. So evidence that we have ice chemistry in this, it's not just in these ice features, there's also a lot of indirect evidence. And we've already seen this particular example of the quaternary disk, where you have the CO emission essentially peaking in the center, and the N2H+, which is a molecule that can only form when CO is frozen out, in a ring around it. So the fact that we detect N2H+ means that CO is frozen out, so there is CO ice. Seems very trivial, but back in 2013, this was the first time that it was actually proven that CO ice is present. And then another sort of indirect piece of evidence is the fact that there were very high abundances of molecular species like methanol or dimethyl ether, these comps, were measured in the gas phase in clouds. But it takes a really long time. It's essentially really inefficient to form these molecules in the gas phase and to wait for molecules to collide and grow larger. However, in the ices, as I mentioned, some of these like buildup of complex molecules is a lot more efficient. And that tells us that the molecules that we're detecting must have formed in the ice, and so the whole presence of these molecules means that ice chemistry must be available. Okay, then switching sort of specifically to the disk. So I also, I feel like I've shown this plot also too many times already. Just a reminder, disks have strong gradients in temperature and density, and this will affect the different molecules, the different abundances that we will find in the disk. In particular, in CO, we will have the surface layer where the CO is frozen associated. So this is a chemical reaction as well. CO frozen out in the midplane, another chemical reaction, and only in between molecular layers. So the combination of temperature and density provides us with the molecular abundance. So this is taken from a review paper from 2 years ago, where they kind of summarize all the processes that are important in this and that can be constrained in a disk related to chemistry. So remember, we have a gas disk and also a pedal disk. They distinguish bare pedals and with and without CO ice. So bare pedals are only inside the snow line. Cosmic rays will have an effect on essentially the composition of the disk, a planet with carbon gap. Stellar radiation from the inside will also have an effect on the outer disk. UV and X-ray radiation. And then on the other side, you see essentially the effects of the water snow line, the CO ice line, turbulence, diffusion. All these radiation fields can lead to photochemistry. So again, additional chemical reactions. Vein evolution, as we've seen, will have an effect on the chemical composition. And so the study chemistry is a complex problem because of all these physical processes, but at the same time it makes it quite a nice challenge. So to zoom out a little bit, one of the open questions for a long time was if this composition was essentially set by the composition of the cloud. And then, all these processes in the disk will change the chemical complexity further, but it wasn't clear if the disk would inherit essentially all the icy dust grains from the cold cloud, if those would actually end up in the disk. Or it may be, so this has also been proposed, in the envelope in the clouds where the temperatures are low, you get this really strong buildup of icy metals, but then by the time that it accretes or falls onto the disk, everything is evaporated again, so there's no more ices. This is also a possible scenario. And then also shocks and centrifugal barriers from in the cloud and close to the disk would maybe destroy the chemical composition of the cloud as well before ending up in the disk. Okay, so these are all the detected molecules to date in photoplanetary disk. Taken from this overview. This guy, I think, writes a new paper every year or every other year where he updates this table. I actually have to add 2 more molecules to this list already. But yeah, so it shows a bit of an overview. Like these are the smallest molecules that consist of only 2 atoms. We recognize a lot of them, like CO, 13-CO, H2, H CS. Then we have 3 atoms, like water, HCO+, H2H+, 4 atoms. So now things become a lot more rare. Like the larger the complexity, the harder it is to detect it generally, because there's simply less of it present. And the largest atom back then was methanol, with 6 atoms. One particular topic of interest, we mentioned it earlier, is ionization of the disk. Of course, this is also relevant for example, the MRI, determining if the MRI can be active in the disk. And ionization can be tracked by looking at ions, for example, HCO+. And there have been several studies where they looked at the HCO+ emission in a disk. And so there's the blue part, that's the data. And then they compared it with molecules with low cosmic rays and high X-rays. How my disk look like? So by running a bunch of different models with different cosmic rays and X-rays, you try to match them with the HCO+. You try to constrain this variation. So this is really a nice example of using chemistry to derive something physical from the disk. Then there is, of course, an almanac survey on chemistry that is called MAPS. I think I mentioned it on the introduction section, where they observed 5 disks in several settings, observing many different molecules. What they found was that there was a large diversity in gaps and other structures in these molecules, and that these gaps don't really overlap with the dust caps. Like some of them do, but many of them do not. And so that means that the variations that we see in molecules are not necessarily related to the gap surface density, because for that they would need to match. So there must be other physical processes contributing to the emission, like both the presence, but also the excitation of those molecules in a certain substructure. And essentially, the conclusion from MAPS was, we don't know what's going on. We need more data. Of course, we always need more data, but I think the main conclusion was like having 5 disks is a little bit hard to do statistics. And they didn't see very clear trends overall in their survey. So yeah, that's actually that brings me to my next slide. This is immeasurable, not new. Also before all that, a lot of this chemistry studies were essentially just looking for molecular lines, deriving abundances, and yeah, not immediately knowing what was going on. And if astronomers don't know what's going on, they plot one parameter, like one measured parameter against another measured parameter, and then they hope to find some correlation, because that can maybe tell us something about the origin of that emission. And also correlations with, for example, the disk of stellar properties. Like here they look at the O1 line, there's some trend here with the stellar temperature. Also here, there may also be a trend with UV velocity of the star, so that may tell you like that line is excited because of based on UV velocity. So this is just something that you often see in these chemistry studies.
Sorry,
yeah.
What are, just to go to the previous slide, what's like the average age of the objects in maps?
They're all like between 2 and 10 million years, 2 and 8, I think. Yeah. They're all protoplanetary.
Yeah.
Okay, then another aspect of this chemistry are ices. And the big interest there is, of course, the snow line, because of the idea that the snow line can enhance planet formation. And this is actually a paper where they state that if you get more efficient correlation at the snow line, that means that you are more likely to form giant planet cores at that location. Sorry, it's really echoing here, so you might talk more quietly, not talk. No, I don't want to be that kind of teacher. Just it's hard to hear myself. Okay. Then another really cool thing about this chemistry is that we can also observe the vertical structure when we're looking at edge-on disks. So this is an example of a study. This is clearly edge-on. You see it's very narrow stripe in the dust chamber. But then 12CO, CN, CS, H2CO all have slightly different vertical distributions. And this means that you're resolving the vertical chemical structures, most likely the temperature structure. You can really see what the abundance are in different layer differences. So this is still really early days. I couldn't really find other papers that did something similar. So yeah, there's still a lot that we can learn. Like we can actually spatially resolve the chemistry and the vertical layers. Well, the snow lines, which I don't need to explain again, where the N2H plus is detected when the CO is frozen out. So originally, the idea was that this was like a very simple relation, but in a follow-up study, 2019, they actually found that the N2H plus emission was a lot more complicated because CO isn't just frozen out in the mid-plane. If you go further away, you actually get the snow surface. So that means that it becomes a lot harder to say like, where does the N2H plus emission originate versus where is the CO frozen out. And yeah, it just meant that the anti-correlation between N2H plus and CO was not as straightforward as we're usually thought. But it gives more constraints than on the temperature structure, of course. Okay, well then about the water snow line. So of course the water snow line is tricky because water circulates at 120 Kelvin. So that's very close to the star, like 1 AU, a few AU. And this is not, so that means that you cannot resolve the water snow line with ALMA. And this is here are some models that show that. However, there are these stars that are known as Upbursts stars, or a few ordinary stars. So they are thought to have bursts of accretion, and because of that burst of accretion, they become much more luminous for a certain amount of time. And it means that they become much warmer, like 100 times brighter than a regular star. And that means that the water snow line gets pushed further out, up to in this case, they, so in this case they look both at the water ice mountains, but also, of course, the CO snow line will be pushed further out, and they were able to measure that with HCO+. So HCO+ is a tracer of ionization, but can also, has been proposed also to be a tracer of the water snow, of the CO snow line. Then complex organic molecules, I've already mentioned that these complex organic molecules are very efficiently formed in the icy layers on dust banks. And this is kind of the process, it's really straightforward. If you have CO ice, you combine it with hydrogen, you get HCO, even more you get H2CO, H3CO, and then methanol, CH3OH. And this is a very old figure, but it's actually really illustrative of how that would happen. So essentially, this process, hydrogen bombardment of CO ices, is the start of complex organic chemistry. So methanol and formaldehyde for a long time were hard to detect in discs. Like TWA Hydra had detection in 2016, finally, but it was very faint, so there was very little methanol present. And in many other discs, in the Ori, it was present, but in most discs, only formaldehyde was found. And the tricky thing here is that formaldehyde can be formed in the gas phase rather efficiently, but methanol cannot. So if you detect formaldehyde but no methanol, that means that there's probably no ice sublimation. And for the longest time, it was thought, well, if methanol may not be present in discs at all, and if it is present, it must be frozen out in the ices, and we will never detect it. But then, about 2 years ago, methanol was detected in the AC-10506 disc. So you see it here. It was an unresolved blob. So I know this doesn't look like a disc. Like a disc looks like this. This is more or less the same scale. And it was just a blob at the right location. And they actually measured that the methanol balance was really high compared to like TWA Hydra or AC-16229. Sorry, the ratio between the methanol and the formaldehyde was very high, which means it suggests that the methanol was indeed formed in the ice phase. And this was a bit of a surprise because this particular disk, AC-100, is a warm disk. It's a very bright star, and it means that you don't actually expect CO ice in this disk. So if you don't have CO ice, how can you form methanol, right? But yet it was detected. So what they proposed was that the methanol must have formed in the early dark cloud stages, like in the ices in the dark cloud, and that those icy petals ended up in the disk, drifted inwards, again, just evolution plays a role, and then drifted inwards towards the point where they were sublimated. So in that way you can have a warm disk, so without CO ice, but with methanol ice. This kind of answered that question that I posed earlier on. Is the disk composition inherited, or is it essentially reset from the cloud and then chemistry down below? This is a clear example of inheritance. And then around the same time, second discovery was made in another disk, Iris 48, this asymmetric one. And here, we also detected methanol and also dimethyl ether, and a bunch of other molecules. And these molecules, because of the higher resolution, were clearly co-spatial with the duststrap. So this was definite evidence that these molecules must have originated from icy layers in the disk, and that those icy layers, or that icy dust grains, must have originated from earlier stages. This is also a warm disk, by the way, like the cloud stages. Ended up on the disk, drifted inwards, and then sublimated closer to the star. Yeah.
Do you have constraints on the cosmic ionization rates for these objects?
No. Why are you asking that?
Oh, because it could be they could still be formed in gas phase
with cosmic rays. Yeah. No, I don't think there are constraints on that. We haven't calculated either how much you would need in order to make that happen. So the interpretation of this particular disk. So here we actually use these rotational diagrams that I was talking about before. So we're able to measure the total column of methanol and formaldehyde, also the temperature, and based on that we could derive that the observed gas emission must originate from higher up in the disk, like where the temperatures are higher, as high as 97 Kelvin. And so you must have some kind of vertical turbulence process that is bringing out the icy waves. And what's interesting is that in other disks, CH3CN and C3N, I don't know the kind of name, but were also detected in this, and they concluded pretty much the same thing. Based on the temperatures of the emission, the emission must originate from higher layers in this, not from the big bang itself. And these molecules were also detected in labs. So now, you may wonder like why these two disks show methanol when people have been searching for methanol for such a long time. One interesting property of these two transition disks is that their dust trap is located inside CO isoline. So there are more dust traps where the temperature, even in the mid-plane, is already above the CO sublimation, and in higher layers it's probably above the other star line. Most of these other disks have their dust traps either further out or their star is less bright. So that means that their dust rings are colder, and whatever is there, it will remain frozen out. So this is one possible explanation. Of course, this suggests that there is really a link between dust trapping and chemistry in the disk. That was actually also. So this is actually another infrared result where they measured the water emission, the scaled by the HCM emission. This is essentially the amount of warm water vapor in the inner part of the disk. What they found is that the strength of the water emission is anti-correlated with the size of the dust disk. And they explain that by the following idea, which is that if you have a drift dominating disk, so this without pressure lobes, all the pebbles from the outer disk eventually end up inside the water strata where they evaporate. However, if there are dust rings where the isotopes get stuck, that means that you will eventually get a lower amount of water vapor. So also here, there's essentially some correspondence. Finally, an important topic of study is the C/O ratio in this. So this is essentially an elemental composition. This is actually proposed as a way to determine where planets were formed. So it was thought that this C/O ratio was a simple step function in a disk. So essentially, wherever molecules freeze out, the local elemental composition will change, and that means that even if the planet migrates inwards later, the original formation location will reflect that local CO composition. And this is actually something that KOST is going to determine CO ratios of exoplanets in order to find out where they're formed. However, you remember this was from this morning, and I think I've convinced you that this is very likely happening in this. So when CO icy pebbles are transported, and actually not just CO but also water and CO2, all of those are frozen out pebbles transported inwards. These are all oxygen carriers, and that means that it will, like the transport of that will change the CO ratio in the disk. In a paper last year, I actually proposed that you can have two possible scenarios, again, whether dust pebbles drift inside the CO line or outside. So if they get trapped in dust rings, the CO ratio in the outer disk will remain large, but in warm disks, whatever gets transported inwards will evaporate again, and then CO ratio will be low. Because this is actually what we are observing in current CO observations. disks. And what this means is that the exoplanet atmospheres are not going to be as simple to interpret in terms of their ionization process. Because say that you have formed two planets that hold the icy pebbles in various parts of the disk, and then accrete their material, your final composition will really depend on like what other planets are also present in the system. So essentially that simple model will no longer work. And I don't have an alternative model yet. It's again something that means combining dust evolution with chemistry models. But I wrote this paper. Yeah, I'm always very proud of this. The title, I managed to get a pop culture reference in the title, and the editor accepted it. It was actually not on the paper list, but feel free to read it. Okay, so to summarize, astrochemistry can help to explain physical conditions and mechanisms in this. This chemistry is particularly complex, but therefore also interesting because of the strong gradients of temperature and density. Aggregation, snow lines play a key role in determining the temperature structure. Detection of complex organic molecules proves the inheritance and also transport of ices in the disk. And the C/O ratio in the disk and therefore also in the planets may be more complex due to the dust evolution effects. So that's what I have on disk chemistry. I'm going to take a little break and then we'll continue with the disk planets.
Should we take the group picture?
Yes.
Vamos a tomar la foto grupal, entonces salimos allá afuera. Tomamos la foto.
I'm about to start again.
Yeah.
I wanted to let you know that half an hour ago, I got an email from the university suggesting people to go early because the traffic will be probably bad because it's like we explained, it's kind of a holiday.
Yeah.
So actually, they suggested to leave at 3, but of course, I mean, we don't have to do that. But maybe we could leave at around 5, maybe.
Oh, you mean in the evening?
Yeah, like I don't know, like maybe if we could dismiss them at 5.
Oh, yeah, sure, that's fine.
Yeah, not at 6 because
Oh,
of the
yeah.
traffic.
No, okay. No, sorry. You were not there at lunch. We talked about that essentially Friday and Zoom is kind of free format, so okay. I don't have a fixed schedule.
Oh, but I mean today.
Oh, you need today?
Yes.
Oh.
Yes.
I didn't know.
No. So the university sent an email dismissing everyone in the university, like from work, starting at 3.
Okay.
So we can stay. I mean, we can stay longer, but I suggest at least that we leave early
Okay.
because of traffic.
Okay, that's fine. That's fine.
5.
No, sorry for. I was like university. That is not till Friday.
Yeah. No. Sorry.
That